any oxygen around. And we needed to have a way to separate nucleation and growth, because it was already known from the 1950s that if you wanted to make crystals or particles of a size that was homogeneous, all the same size, it was one of the ways to get it was by having an event where you create very small seeds of the material, and then a slow growth where you grow on top of the seeds. This was known for bigger particles, for micron size or millimeter sized particles by Lemaire and his co-workers in the 50s. And you can see this in the world around us where, in Cambridge, it snows. When it snows, the snowflakes, they might all look different, but the size of the snowflakes are pretty much all the same. So if it's wet and humid and close to freezing temperature in the atmosphere, the snowflakes tend to be big and fluffy. They're all the same big and fluffy size. If it's very dry and very cold, the snowflakes are all really tiny, right? So the crystallization of the snowflake happens by forming seeds, very tiny seeds in the clouds, tiny, tiny micron-sized seeds. Then they come down through the atmosphere and they aggregate more and more water molecules. And so the conditions of the atmosphere result in, by the time it gets to the Earth, particles or snowflakes are kind of all the same size, depending on the processing conditions. So we had to replicate that. Nucleation and growth. So we invented this very simple process, which is now called the hot injection method, where we start with metal organic precursors that contain the elements that we need to make our particles. Those metal organic precursors are stable at room temperature. This was inspired by process engineering of semiconductors, MOCVD, metal organic precursors that were used in these processes. Then we inject them rapidly into a solution which is at high temperature for organic chemistry being on the order of 300 degrees Celsius or so, 350 degrees Celsius. In the presence of the high temperature, these metal organic precursors crack, or they decompose, liberate their elements, and these elements can then react together to form little tiny seeds of the semiconductor that we've chosen to grow. This solvent at high temperature contains other molecules, other organic molecules that can bind to the surface of the growing seed to prevent it from growing out of control. Then once this nucleation event happens, then we have a slower growth where we can monitor then the growth. And when we have the size that we want, we can just stop the heat and we're done. So it's a very, very simple process, all done under nitrogen. So now, this is now a little later in the 1990s. There's progress in technology. Now, instead of having to write everything with a pen, we have a laser printer. The laser printer appeared, the early 1990s. So it's a mixture of laser printer and writing. But you can see the ideas are there in my 1993 transparencies, 92. The idea of nucleation and growth, of the high temperature, and organometallic precursors that are stable, that react, and then the extraction of the material as a big molecule using methanol at the end of the process. So we went ahead and later my students put together a YouTube video of the process. This YouTube video happened in 2010 or so, but it's still done the same way. So there's a quick injection. You can see the color change. These are the small seeds that are about a few nanometers in size. And then if you wait a little longer, the growth happens. And we're going to skip 20 minutes here. The color is going to get darker because the cavities are now bigger, right? The cavities are bigger. So these are now 5, 6 nanometers in size, and you can see the change in color. You dilute them, and then you can really see how the particles have grown. So this is at 350 Celsius. The process has been now scaled up in companies. And instead of doing it in a little flask, it's done at the 3,000 liter scale, huge scale. Now you can see the different emission of light coming out of these things. So this process, which in the lab, you do it manually and you get this nucleation and growth. And I never thought at the time that you could scale this up to anything bigger than that, right? But, I visit these plants, they do the same thing in huge, huge steel containers, all automated. And it's just incredible. You come in with precursors at the beginning of the process, huge automated process at the end of the day. There's a barrel of quantum dots that comes out that's purified and very, very high quality. So we wrote a paper on this in 1993. And that was my first paper as an assistant professor. So I started in 1990. And for 3 years, I didn't write anything. I didn't write any papers because we were working on making these particles. And today, my colleagues at MIT, if you have an assistant professor that doesn't produce any papers for 3 years at the beginning, we think there's something wrong with them, right? They're going to fail, right? They're just not on the right track. But that was okay because, I was used to not caring about what people thought. I wanted this paper to be a really good paper. My student, Chris Murray, along the way, thought we should publish earlier. He said, he really wanted me to write it up. And I told him, the world does not need another way to make bad quantum dots, right? We could have written a paper, but so what? Wouldn't have achieved anything. But so I wanted this to be really, something that would make a big difference for us in the field and allow us to do the physics. And so there's a number of words that I've underlined here that turned out to be important. I didn't realize that at the time, almost 40 years ago now, 30 years ago, actually. One of them is that it was simple. It was a single reaction. And we have a process that we call size-selective precipitation. That's a fancy word for saying we purify the material. If you're a chemist and you make a new molecule, you need to purify it so that you can characterize it and then you can use it to do further chemistry. These nanomaterials, we didn't really know how to do that yet. They were not molecules. You couldn't crystallize them. You couldn't do play with solvents to do these sorts of recrystallization techniques. You couldn't put it through a column to isolate them. And so we created this simple process to basically get them out of solution, to remove the other byproducts, and to really purify the material. So simple and purification. The paper also talks about characterization, because it turns out that you have a new nanomaterial, you need to characterize it in so many ways. So we talked about using electron microscopy, X-ray diffraction, all the tools that today are the standard tools when you have a new nanomaterials that you characterize to really understand it. And one of the tools, because these are optical materials, was just to do simple absorption and emission properties. And you can see here in this spectrum, in absorption, now we see multiple peaks. What are these peaks? Well, the peak that is the closest in the reddest is the fundamental, right? It's like in music, it's the fundamental frequency of your flute or your string instrument. Then the other two peaks that are a little further in energy, and bluer in color, those you can think of as the harmonics of the system, right? So they're higher energy peaks that are harmonics of the fundamental. And then you have the emission peak, the one single peak, which comes straight out of the material, which depends on the size of the material. And for the first time, for these materials, we actually saw emission that was, I thought it was bright, and it was, the color was quite narrow compared to other materials, and we call that saturated. The color was saturated. And I was so excited that, I thought it was so bright. The quantum efficiency was 20%, which means that only 20% of the photons, the blue photons, resulted in after being absorbed in a photon of a different color coming out. So, and this was much better than before, because before the quantum efficiency was 0. So this was infinitely better than before, right? So 20% was infinitely better. So I had a colleague in Germany, and I so excited, these are so bright, 20% efficiency. He told me, well, what that means is that 80% of your sample is terrible. And he was right? We weren't done. 20% was infinitely better, but it wasn't quite good enough yet. Today, it's 100%, okay? And I'll tell you about that. In his thesis, Chris Murray, this comes from his thesis, this graph here, and you can see then as a function of size, you can watch these harmonics change, the position of these harmonics change, and then you can have a series of samples, and what you see in this series of absorption samples is the difference between any two of these spectra is maybe at most a couple handful of atoms that we're adding to the surface. So this really showed the exquisite control of the size that we had with this very simple process, right? Exquisite control at the atomic scale. So now I wanted to do physics, right? So we had set this whole thing up. I wanted to do physics, see how the properties change with size. And as a physicist, when you want to see beautiful things happen, you often go to low temperature. So we went to 10 Kelvin, where things sharpen up and you can really see things out of the thermal noise happen. And this is an experiment on this part right here. So the x-axis is size. You can see it says decreasing radius on top. So small particles are on the right here, and big particles are on the left. And what you see is these harmonics getting closer together as the size gets bigger. But something happens at one point. These harmonics start to deviate from coming together monotomically, right? And in spectroscopy, we call that an avoided crossing. The harmonics, the energy wants to cross, but it can't. That's a very fundamental quantum mechanical signature of something. In this case here, it's a signature of the fact that one electron in that box is beginning to see all the atoms that exist in the box. It's beginning to interact with these atoms. So you're going from a process where the box appears to be empty in terms of the electron's perspective, to the electron beginning to see that, wow, there's a lot of atoms in there, and I'm scattering off these atoms in a way that's scattering of the crystal in a way that is now what we call coherent, right? And so that is a property of the bulk material. So that tells you that this is where this property begins to go from the atomic to the bulk for this particular properties. And there's so many properties of material that you can study this way, and every one of them, starts to see the bulk properties at different rates. We also saw that these materials then could be assembled because they were all the same size. They're kind of like big atoms, right? And if you take a bunch of atoms and you take them together, they can assemble each other into crystals, right? And so these we're assembling into superlattices or supercrystals. And these supercrystals today are an active research area, because you can think of these particles then as artificial atoms. We're creating material that has quantum properties, and then we're combining them together. So it's kind of a new periodic table. We can bring them together. We can bring different kinds of particles together, mix and match their properties, and try to see if there are new properties that come out through them talking to each other. So there's a big community that's working on this now. This is Sherry Kagan, one of my early students also, who is still working in this area as a professor at Penn. A big advance in the field came, so let's go back to the timeline. The discovery of the quantum effect, size effect, was in the early 1980s, 78 to 82, something like this. And then it took about more than 10 years for the synthesis to catch up to the idea of the size size, the properties changing with size in a very characteristic way that we could really study. So 10 years of searching for the synthesis. 1993, we had that breakthrough. We published our paper. And then suddenly the community started to grow because we had a material, a field where you could actually do something. You could study physics and you could start thinking about what to do with it, right? So that was 93. And very quickly, we, as well as other members of our community, then started to figure out, okay, so 20% quantum yield, that seemed bright, but it's not good enough. Let's do something about this. And it only took a couple years then to figure out how to get that quantum yield up. And that was by making what we call today core shell particles, where you take your quantum dot and you surround it by another material, a higher bandgap semiconductor, to protect it. It's like an M&M, it melts in your mouth, not in your hand. So we're protecting the quantum dot from the surroundings. So now we have this material, which is our functional material in the center, surrounded by another material to protect it, and then organic molecules to allow it to be manipulated like a big organic molecule. Okay, so that became sort of the engineered material that we're used to making today. And the quantum yield then went up to nearly 100%. Around the same time, fields are not in isolation. Around the same time, early 1990s, there was the growth of single molecule spectroscopy, where people started to be able to observe single molecules in a fluorescence microscope, the light coming from single molecules. That ended up being a Nobel Prize. W.E. Murner was awarded that a few years before my Nobel Prize. And so because I was really interested in light and molecules and quantum dots, I thought we have to be able to do that with quantum dots. We have to be able to see single quantum dots. That will be amazing because every dot is different. But if we can see individual ones, then we can cut the noise of the distributions and really begin to understand the physics. So that's when we started to do these single quantum dot spectroscopies, and these core shell, bright, stable dots allowed us to do that. And one of the things that we observed immediately when we looked at single dots is that they were not stable. They blinked on and off. And why do they do that? It's because they're interacting with their environment. They're little sensors, little nano sensor of their environment. And what we're seeing here basically is a charging, discharging of these particles, right? Today, we've learned to harness this effect. We can make them super stable so they stop blinking, or we can make them so that they interact more strongly with the environment to really become sensors that we can manipulate. When they're very stable, now today, my experiments at this level of single quantum dots, our interest is in quantum information, because these are very tiny particles that can emit very special kinds of light that we can use for quantum information processing. So we're still using these same sort of experiments with the same sort. We were chemists, right? And we chemists, and to us, the closest field to chemistry that we can think of to apply these materials was biology. These materials were on the same size as big proteins. People were using dye molecules to tag cells and to do fluorescence experiments in vivo to watch things. And we thought as a community that, well, these little quantum dots are more stable because they're three-dimensional pieces of rocks than dye molecules. So we should be able to use them for tagging cells. And in fact, the first company that was created using quantum dots was created in 1998. Just 2 years after the creation of the core shell particles, 5 years after the synthesis, but 15 years after so you see the timeline. The curiosity needs to, there's an induction period that can last a long time until you have an explosion of growth in the field and application. So the first company, Quantum Dot Corporation, was created in 98. This is an image where the red is light coming from quantum dots, the nucleus of the cell, and the green is from dye molecules photo bleaching away. Today, this is part of Thermo Fisher. We went into in vivo imaging, the interaction of these nanomaterials with animals and humans. How do you transform a nanomaterial so that it can be biologically interesting? So we learned to coat the surface of these nanomaterials with what we might call biological Teflon, with PEG groups, attach antibodies to them, for instance. And this is an experiment. This is a 3-color experiment with quantum dots of 2 different colors to look for this is in a mouse model, to look for special cells, rare cells that are kind of like stem cells. And in this case here, these cells have 2 different receptors that are overexpressed compared to normal cells. So we can come in with these 2 different color dots, red and blue dots, and they find these special cells. And then in your microscope, you can look for yellow because green and red makes yellow. Then you can find, in this case, this special cell, this special yellow cell. And then you can start to study its microenvironment and understand a little bit of biology. One of the things that we also discovered was that these dots, the color of these dots depends not only on the size, but also the composition of the material. So by changing the composition, by going, let's say, from the silicon or cadmium selenide to some other semiconductor, in this case, indium arsenide, we can make light that's further into the infrared and with still fairly good efficiency of emitting light. And then we could use that in biology because organic molecules have very poor emission in that color. So now we have something that can be excited and that can emit against a black background. So with better signal to noise. And this is an experiment that we did looking at, in a mouse model, looking at, in this case here, the green color that you see is a glioblastoma. It's a tumor in the brain of this mouse model. And then you can see the veins in blue and the arteries in red. Then we created these composite particles made up of quantum dots. The whole composite particle is about 100 nanometers in size, which is small enough that it can go into the blood stream of the animal, but big enough that we could actually see them individually in the microscope. And so when you do that, you see the bright spots in the microscope. On the left side here is the tumor, and on the right side here is the healthy brain. Then you can see that in the healthy brain, these bright spots flow very quickly. That's what normal flow should look like. But in the tumor, the flow is disrupted. You see bright spots that aren't going anywhere. They just go back and forth. And that visualizes why it's so hard to treat. One of the reasons why it's so hard to treat solid tumors, because it's hard to get therapeutics in there. It's hard to get oxygen in there. That's why the tumor environment is acidic. It's full of carbon dioxide. And so our collaborators in the hospitals, they want to make the left side look like the right side so that the therapeutics can be more efficient. So these are the sorts of experiments that we did. It's not until a little 2000 now. So the biology started in 98. By 2002 or so, we started talking to electrical engineers. And this also was the invention of the gallium nitride blue diode. Nakamura won the Nobel Prize for that. The blue diode, solid-state diode, that has revolutionized lighting, right? The efficiency of light bulbs has increased tremendously because of the use of these blue diodes. That was discovered in the early 1990s. And we realized quickly then that we could combine our quantum dots with these blue diodes to create different colors. So the blue diode, you excite at 465 nanometers, and all the colors of the dots can be then absorb this blue light and emit different color lights. And so that was the creation of 2 companies in the early 2000s, Nanoscience and QD Vision, both combination of MIT and Berkeley and other universities coming together. And both are now part of bigger companies. Nanoscience is part of a Japanese company called Shoei, which makes quantum dots in very large scale. QD Vision was acquired by Samsung. And the first product that came out of those thinking about electrical engineering and color and and displays and lighting was these LED light bulbs. But this was early 2010, really. So when the cost of each light bulb was about $100, and they were too blue. There wasn't enough red in them, so that if you use them in your bathroom, you would go back to bed because you would like a ghost, right? You wake up in the morning, you look at yourself in the mirror, and you say, oh, and you go back to bed, right? So it needed to be warmed up. And one of the ways you could warm them up was by adding some quantum dots to absorb some of the blue light generated by the gallium nitride diode and make red light. So this, as a technology, this worked, right? There's still light bulbs like this in my office. They work just fine. But financially, it turned out to be a mistake to use them for this application because, as long as they're $100 a piece, then you can add quantum dots and make some money. But when the cost drops down to $10 a piece or $5 a piece, there's not enough margin to add quantum dots to them. And so the companies, QD Vision, had to pivot. They had to change direction because this was not going to be a financial success. And they realized, along with Nanosys, that a better application financially, although using the same idea, was in displays, where you wanted to take blue light and create new colors. And the first product that came out then was by Sony. And the idea was to take these blue LEDs, absorb some of the blue light into quantum dots to make green and red light in the back of your LED display, your LCD display. And Sony came out with a product in 2013. I have 2 of these TVs still, more than 10 years later. They work just great. Sony only used these for 1 model year. Why? Not because it was a bad technology, but because QD Vision, who had partnered with Sony to make the DOS for them, was a startup company, and they had promised Sony that they would scale up from making 1 piece at a time to making 1 million pieces so that they could sell millions, and they couldn't do it. Scaling up is really hard. You have a process that you can do by hand. You try to scale it up, and it's really hard. So that was a failure of thinking of how to do that. But in the background, Samsung saw this and thought this was a great idea, and but they didn't like cadmium, so they invented and also Amazon came out with a Kindle in 2013 using the same sort of technology, using Nanosys technology. Samsung went ahead and invented indium phosphide quantum dots, how to do that chemistry without cadmium, and figured out how to do the scale up, how to go from pieces made by hand essentially to scaling up into these huge 500 and eventually 3,000 liter containers to do the same chemistry. That was really hard. It was very expensive, hard and expensive, but they did it. And they bought QD Vision. But when they bought QD Vision, part of the acquisition was actually to buy the trademark QLED. Because if you look at that trademark and you get rid of the tail on the Q, what does it spell? It spells OLED, organic light emitting diode. And LG, their competitor, was selling OLED displays. And Samsung could do one better. It wasn't OLED, it was QLED, much better. Right. So that trademark was worth tens of millions of dollars, to Samsung. Today, the technology is that you start with blue OLEDs that are pixelated, and you inkjet print on top of the blue OLEDs quantum dots to make the other colors. And the October 2023, when the Nobel Prize was announced, the same day, I got an email from Samsung Display asking me where I wanted my new QD enhanced OLED television delivered. And I said, give me the biggest one and bring it to my office. Now, you have to know a little background to this story. When Sony came out with the QD television first, I asked them to send me a television. And they said, no, you have to buy one. I asked QD Vision to give me a television. They said, no, you have to buy one. So it took me 2 years to wait until the first Sony TV was on sale on Amazon. to buy one. But here, the Nobel Prize made a difference, right? Within a week, I had a beautiful new display. So the same idea of color down conversion, going from blue to different colors, is now being used throughout. This is a very simple technology. It can be used to harvest the sunlight to create red light or different color lights that you can then use either with photovoltaic cells to create electricity, or one of the applications today is to use it in agriculture. It's known that certain kinds of plants give better yield if they have more red light compared to blue light. And so you can build greenhouses that are covered with films of plastic that contain quantum dots to improve the yield of tomatoes, for instance, or different plants. And so it's all about cost. And the cost of making these quantum dots, because it was a simple process with now some elements that are abundant enough, the cost has really come down so that these applications really have a chance. This is another simple application of taking an infrared camera and making it be able to see the UV or the visible. So this is a video that my students and collaborators had fun making about 10, 15 years ago, or 20 years ago, I guess now. So if you have a camera that sees in the infrared, it cannot see in the visible or the UV because it's made up of indium arsenide. Visible light is the sensor to see visible light is silicon. So if you want to see both the UV and the infrared, you need to carry two cameras, a silicon camera and an indium arsenide camera. What if you want to see everything at once? So it turns out there's a very simple way to do that with quantum dots. You put a small layer of quantum dots on top of the indium arsenide sensor. It absorbs the blue and the UV and transfers that color to the infrared. So what you see here on that screen is my student and Frank Jaworski, he was working for Raytheon at the time, reenacted a scene, a spy scene. Maybe this is a spy scene in Berlin, in the 1960s. And they're exchanging secret documents, right? And there's another spy that wants to keep track of which briefcase has the secret documents. And he's put a little UV tracker on one of them. And he's using a night vision camera to keep track of everything happening. And so this little tag that you see on there, so Frank is going to pick up that briefcase with the secret documents. And the camera, the sensor, has coated with dots on one side, which is why you see the UV. And then as he walks across, this side doesn't have any dots on it. It's blind to the UV. So a very simple technology that can expand then the color range of these simple sensors. Today, we think about going directly to electroluminescence to make lighting and displays, photovoltaics, night vision cameras, all sorts of applications. And so where are we today? The field has expanded tremendously. It's now a real community. I never thought I would be part of a community. But now there's this huge community of people, right? We work not only on semiconductors, on metals, semi-metals, magnetic materials, using similar kind of chemistry concept from 1993. The same ideas of characterization that we proposed back then. And then we have different morphologies. We have these core shells, but we can also make rods and helical materials, and we can combine them all together into assemblies, because now we have this whole building accessible, all these building blocks accessible to us to create new materials. And they're real applications, that are being used by people all over the world. Not just in displays and lighting, which is a huge market where most of the dots are used that are being manufactured for that, but in biomedical imaging. It's a research material that's being used all over the world, not just in imaging for biomedicine, but also for sensing, for diagnostics. Light sensing, as these infrared sensors that I showed you, is a number of startup companies are trying to commercialize that in solar energy, in agriculture. I didn't talk about certain photovoltaic aspects that are also being commercialized by big companies like First Solar. The emergent applications in catalysis and photocatalysis that the field was based on back in the 1970s and 1980s, early 1980s, are coming back. And solar to fuel is a concept that uses nanomaterials of all sorts. And I know that Professor Vinu is very active in that direction. So, and then in electronics, in my own work, in quantum information, quantum systems, in optics. So the future is still opening up for these nanomaterials. And these nanomaterials are only a little tiny piece of nanoscience, right? So nanoscience has really exploded, and it's really all around us in ways that we don't even realize, and will continue to grow and change our world. Okay, I want to thank all of the students because they're the real heroes. There are about 150 students in my group over the years, and that takes a lot of money. And the last thing I want to say is, I've been asked over the years, these last few years, to a little piece of advice for young people, and this is what I came up with very quickly. Stay curious. Stay curious because that's where innovation comes in. Keep learning because you want to connect things together and to move forward. Be flexible because research is really about failure, overcoming failure, changing directions. Don't give up because eventually you'll figure out how to do it, and enjoy life while you're at it. Thank you.
Thanks, Professor Bawendi, for your inspiring lecture. Now the talk is open for discussion. So if you have any questions or comments, just please. Yep. Nirmala, yeah.
Thank you very much. Excellent talk. No question, actually. I'm really curious to know two things. One thing is that we say in quantum confinement from 3-dimension to 2-dimension, then 1-dimension, 0-dimension. We say 0-dimension is a quantum dot. Still, it is 1.5 nanometer to 3 up to 4 nanometer, even depending on the material. My curiosity is that why we say it is 0-dimension, whereas 3 nanometers says there in all direction. This is one I'm curious to know. Another thing you mentioned, this single quantum dot, the light it gives. That you mentioned also in 1919, Shuji Nakamura, this blue light, 450 nanometer. What is the wavelength of this light of single quantum dot? It's supposed to be lesser. You have not mentioned it. That's a new light. Single quantum dot light and that blue light, the new light, what is the wavelength? These two things I'm curious to know.
Yeah, so the first question was about why 0-dimensional. So because a 2-dimensional confinement is a 2-dimensional quantum material or quantum well is where the confinement is only in 1 dimension. So in 1 dimension, let's say the z direction, the wave is squished and you see the wave properties of the electron. But the other 2 dimensions are very big dimensions, and the electron acts like a normal particle. So it can move around in 2 dimensions as a particle, but in 1 dimension, it's confined. So that's what we call a 2-dimensional, a 2D, like a quantum well. 1D would be if it's a wire. So the particle is free in 1 dimension, and it's confining the other 2. The quantum dot is confined in all 3 dimensions, which is why we call it 0D material. The other thing is the color of the special light depends on the quantum dot, right? And so, and actually, the quantum effects aren't just in the nanometer. We've discovered that we keep, in fact, Alexei Ekimov knew this back in 1983. You can go all the way to 100 nanometers and still see quantum effects at low temperature. So it's not just the, really a few tens of a few nanometers, but really huge things like, to me, huge is 100 nanometers. these things can also show quantum confinement effects.
Yep. Professor Raman from Monash University.
Thanks, Vinu. Always great to be here at conferences where you are involved. Professor Bawendi, Raman Singh from Monash University in Australia. The systems that you talked about, as opposed to carbon-based systems like graphene oxide, carbon nanotube, carbon nanodots, and all that, how do they compare in terms of their applicability in real life? You have been very successful in doing research and also implementing it into industrial domain. How do they compare?
Well, they're different properties, different materials. So, graphene, thin films of graphene can be used to coat things, to transport electricity, to have all sorts of really interesting properties. So it's a really different area of application. The dots have their own, especially when you talk about light, the light-matter interactions. The graphene and all these other materials are more electronic materials.
Good, thank you.
Yeah.
Good morning.
Yes.
Just small question. In microbiology, we are using fluorescent microscopy. There's some, based on the stain, we can able to differentiate bacteria into dead and live, viable and dead. But what type of stain, sir, you are using in your research?
So you said you can't differentiate between live and dead
cells.
bacteria.
Yes.
And
But you have used fluorescent microscopy, but checking the quantum dots. So what type of stain you have used to compatible with that particular material?
so I didn't quite, what stains
Stains, what kind of quantum dots that he used to come to differentiate?
to differentiate between live and
Yes.
dead?
Yeah.
So, this is not a question that we tend to ask, is it live or is it dead? So I haven't really thought about, what kind of quantum dots. I would say probably we would attach different things to their surface that would interact with bacteria in different ways.
Yep. The student, yes.
So good morning, sir. So I'm an undergraduate student in electronics engineering, VLSI design and technology. And we actually have many courses related to electronic materials and physics of semiconductor devices. And we have been exposed a lot to these new concepts of quantum dots, etc. And with what we learn about transistors and how in the small scale, at the scaling level that we've brought on, and we have these quantization effects and how these quantum size effects itself affect us, this field itself. I wanted to know your insights on how these two fields, this interdisciplinary field between your field and maybe this VLSI domain itself, how they can be connected, your insights.
Sure. Yeah. So back in the 1990s, one of the motivation for this field beyond curiosity was what happens when you take a computer chip and you make the circuits smaller and smaller and smaller, will these quantum effects change the way that we have to think about chips? And, at the time, the length scale of chips was on the order of 100 nanometers or so. So it was right at the edge where quantum effects that we were studying. And so we wanted to study that. But it turns out that you can go much smaller in chips without having to worry about quantum effects. Yeah, so we go down to 3 or 4 nanometers that are now in chips, and we still can treat them, quite classically. But you can use quantum effects in specialty semiconductors to your advantage. So you have a toolbox, that you can use. They can either behave classically or quantum mechanically. So it's a new toolbox.
Yep, thank you. So I strongly request you all guys to ask a short question, right? Yeah.
Thank you for a nice lecture. Thank you for coming.
Yes.
Yes.
I'm a graduate from the University of Sydney. The quantum effect size, it leads to many property improvement in many fields. But in case of perovskite solar cells, the power conversion efficiency and stability of quantum dots are still lesser than the normal material. may I please know the reason? Do we need further optimization?
Okay, so
Yeah.
I also work in perovskite quantum cells, and for those, we actually don't use quantum dots because it's a question of economics. I mean, for solar energy, you want it to be as cheap as possible, and a thin film of perovskite is much less expensive than making quantum dots and using those to make a solar cell. So we use thin film perovskites. The progress in that field has been tremendous in the last few years. The stability has gone much better, and it's beginning to look like it's going to be a real technology.
Okay.
Yeah.
Thank you, Professor, for your nice lecture. My question is,
Here.
Yes.
right, thank you, Professor, for your nice lecture. My question is, I saw one of your slide, there is a red emission. That means your quantum dots makes any FRET effect. That means fluorescence, resonance, energy transfer. Like I saw all your absorption and emission spectra, which is overlapping. So when you use solar cell, you are making, which is the FRET effect. That means fluorescence, resonance, energy transfer effect. Is it or any other technique you are using?
So yeah, so FRET, fluorescence resonance energy transfer, is something that we use purposely for some effects, and other times we try to get rid of it, and we can get rid of it by getting that emission to be farther away from the absorption so that we can eliminate it.
Yeah.
Just.
Thank you. Thank you. It's a wonderful talk. So I have two short questions. One is from.
Just one question. Okay.
Okay.
These other people are waiting. Just
One question is.
short question.
Yeah, you mentioned that the part of the reason behind your success is that you are part of a field that was just still emerging. And for the graduate students here, do you still recommend people to work on quantum dots because it's already very saturated, or I would say it's more settled and there are a lot of community here. So do you still think it's a good idea to work on quantum dots or?
Well, there's still so much to learn and so much to do with these sort of quantum dot materials, and I'm always amazed when I go to conferences, the innovation, and that is in the field, the new discoveries. So I would say it's still an open field to go. But my advice for the graduate students is, if this is what you really like, then certainly go for it. But don't feel like you have to work on something because everybody else is working on it. You have to do what you feel is the most interesting to you rather than what everybody else is doing.
Yeah, please.
Sir, my name is Ashutosh Mahajan. I'm faculty in CNR. So my question to you is, you spoke about quantum information and application of quantum dots towards qubits. So is it, how do you see the future? I mean, compared to TMDs are also used as a possible candidates. I mean, in the next, in the coming decade, how do you see the future of quantum dots for qubit formation and towards room temperature applications?
Yeah, it's still an emerging material for that. There's still a lot of work to do. So from my perspective, we're interested in studying, the fundamental properties of the material and how to shape it, how to engineer it. So I can't predict 10 years from now, what it's going to be, if it's going to be useful. All I know is that it's really interesting to me right now, and we'll push it as far as we can.
Yeah. Yes. Excuse me. Yeah.
So I'm Bari Shankar from IIT Chennai. So I told based on the biomedical application for the tumor cells, what type of tumor cell is detected based on the quantum dots application, sir?
What kind of tumor cell?
So biomedical imaging of processing using the tumor cell is told for the applications for the quantum dots. So what type of tumor cell detect based on using the quantum dots applications?
So we studied mostly generic. So a lot of the work we done was with glioblastoma, but that's just because our collaborators were working on that. It's really kind of generic.
Okay, thanks.
Yeah,
Just-
Professor, my name is Sendil Kumar from Department of Chemistry, Vellore Institute of Technology. Professor, very nice talk. We are blessed to hear your talk in VIT Vellore. Thank you very much. Professor, gold nanoparticles now already well known for this kind of effect. I'd like to know how this gold nanoparticles differ from your cadmium sulfide and selenide. Already 1850s Faraday already discovered this kind of gold nanoparticle, and
Yes,
Maybe at the time it is not mentioned as nanoparticles, it's a clusters.
yes.
Clusters. So how this your inventions it's differ from this classical gold nanoparticle systems?
Right. So, the gold is a plasmonic effect. The color is from a plasmonic effect. It's an effect due to many electrons behaving together, as opposed to a single electron, showing these quantum properties. So in a way, you can think of the gold effect as more of a classical effect, a plasmonic classical effect, than a quantum effect. But, so you can use the technologies of making quantum dots to make better gold particles
Yes.
so that they have enhanced properties
Yes.
compared to the ones that Faraday made.
Okay, thank you.
Sir, in the middle.
Yep.
Sir, I am a student from VIT, and I asked this question on behalf of all the students here. I noticed that you said that you scored low grades at the start of your semester in Harvard, and you felt like that was the end of your career. So, would you describe your mindset and motivation, especially when you were a reserve person, on how you came back to be such a great person that you are today?
Huh. Well, I would say that I really liked science, I really liked chemistry, and I really wanted to do that. And I thought about why I had failed, and it wasn't because I wasn't smart enough, it wasn't because I didn't know the material, it was because I didn't know how to study. And so I learned very quickly how to study studying for an exam is not the same thing as doing research, right? It's a different kind of mindset. You need both. You need to be creative when you do research, but when you do research, you also have to have knowledge behind you so that you can connect things together, so you can understand things at a fundamental level. And that's where the coursework and studying for the exams on the coursework is helpful, because it allows you to really internalize these concepts. So I needed to learn how to study, was really what I needed to do.
Yeah.
Hello, sir. I am Bornali Maiti from VIT Chemistry Department. My question is that what is the difference between nanoparticle and quantum dot? Because quantum dot means 1 to 10 nanometer and nanoparticle more than that. What is the size difference?
So I didn't.
What is the difference between nanoparticle and quantum dot?
So a quantum dot is a kind of nanoparticle, right? It's a nanoparticle made of a semiconductor, but you have nanoparticles of all sorts of things. You can have particles made out of oxides, silicon oxide, for instance, or metals or magnetic materials. And so now there's a toolbox of all sorts of materials that have optical properties, magnetic properties, structural properties, you name it. And we can combine them all together to form new materials.
Quantum dot means 1 to 10 nanometer, that sizes we can say the quantum dot. Any particle.
Excuse me. No follow-up questions. So you ask the questions, give the chance to others. Yeah.
Sir, I'm a PhD student. I'm work on quantum dots. I have a question on how what properties of quantum dots should be focused and enhanced for the quantum information career.
So if you were interested in using dots for information theory, for information as quantum information processing, you have to look at their optical properties, the photons that come out. And the word that's important is coherent. You want to have coherence in the photons that come out. And that's the most important properties. And we want to go to low temperature, to cryogenic temperature.
Does defects in quantum dots play any role in that?
Yes, I didn't hear the question.
It's fine. Yeah. Excuse me. Yeah.
Hello, sir. I'm Kaushika. I'm a research scholar from Siena. It's my great opportunity to meet you and interact with you. It's like there are various biomedical applications. We are using quantum dot for many type of biomedical application. How you will fix the concentration of the quantum dot based on that? Is there any particular protocol or any other ways, like how you will fix the concentration?
So that's a very detailed technical question that I think I can't really answer too quickly.
Yeah. See, the ask questions that should be, I mean, kind of advice or the future. It's not this kind of, yeah, it's fine.
It can be done. It can be done. Is the
You
answer.
you can follow, you can read his papers. I mean, if you want those kind of questions, yeah. So answers, so maybe another few more questions, so.
So, over here.
Yeah, please, yeah.
Yeah.
Yeah, at the end.
So, my question, I would like to know your perspective as a scientific mind. It's not directly related to your work as such. However, nowadays, we see that despite there being a lot of scientific basis and research for a lot of environmental concerns or concerns related to science and technology, a lot of prominent people or organizations do not believe that these are tangible concerns which should be addressed, and that delays scientific progress. So in such a case, in such a situation, how do you believe we should proceed with scientific innovation?
I'm not quite sure I understood the question.
Yeah. Nowadays we see that despite there being a lot of scientific basis and research about a lot of concerns, such as environmental concerns, there are still very prominent organizations and people, especially people in power, who don't believe that these concerns should be addressed.
Yeah, okay, well, I'm a strong believer in science and science helping humanity and helping us to solve the problems around us. And sometimes economics interests seem to prefer to ignore science, and that's to the detriment of humanity. So I'm a very strong believer that, scientists should speak out and make sure that our voice is heard when we see understand things like climate change, for instance, that that the human impacts on our environment. So these are things we understand as scientifically, and it's our job to speak out, on these things.
Yeah, thank you. Last two more questions. One is from here and then the end. Short question, please. Yeah.
Good morning, sir. So for young researchers working at interdisciplinary boundaries, how should curiosity-driven research be balanced with application-oriented goals? So you have started your research from the curiosity. So how it will be helpful to attain the goals, and what are the things you have done?
Okay, so for me, and everybody is different. Okay, for me, the journey was really a curiosity-based journey. And once we discovered the new materials and the new properties, we started to ask the question, what are they good for, right? And that led to the application. You can have an application in mind and say, what could I use for this application? That's a different question entirely. And then that's more of an engineering problem. So, it's a different mindset and everybody's different. So, I would say follow your interest.
Yeah.
Thank you, Professor, for the insightful talk. I'm a research scholar working on graphene quantum dots. As we see changing the size of the quantum dots, we see different emissions because of quantum confinement effect. My question is, at extremely sizes, is the color governed by the size or surface states or ligand interactions that dominates the emissions?
Yes, so certainly, because these materials are mostly surface, the surface can have very strong effects, and you can use those effects as well as the size. So it really depends on the material, and you just have to study them and figure out, which part you want to harness.
Thank you.
Okay, the last question. Yep. Sorry.
A very good afternoon, sir. Thank you for the insightful talk. I'm Toshika Mishra, working under the guidance of Dr. Smita Buppu, Dean SPST. My question is, which application of quantum dots do you believe holds the maximum or greatest long-term impact?
So the application with the greatest impact. So it depends. how you define impact. So, the application with the greatest financial impact is in displays, right? The application that is the closest to my heart may be in biology. And the application that's closest to my brain intellectually would be in quantum information, which is much further in the future, than the displays today.
Thank you, sir.
Yep. Thank you. Thank you, Professor Bawendi, for your insightful and inspiring lecture. And he has beautifully demonstrated that from his personal story, that the failure is a stepping stone for the success. And then he went on to get the Nobel Prize. I mean, that is quite inspiring. And he also demonstrated that, more elegantly, if you can finely tune the size of the nanoparticle, and that can lead to new properties of the materials and new technologies that can produce the new science and technologies that can change, or support the world and the society. With nanomaterials, this is not merely just size, but it has got a huge impact. I mean, he mentioned that the impact is immeasurable. It depends on what kind of impact that you are talking about. The impact that he has made, from developing the screen displays to the drug delivery system to energy storage and conversion. Now the perovskite solar cells, and that has made a huge impact on the world and the society, right? I mean, this is how every researcher should dream of. I mean, if you can just link that, the fundamental curiosity when combined with the precision and perseverance, I mean, of course, that can produce a wonderful science, and that can make a huge impact to the world and the society. So on behalf of the conference organizing committee members and also the scientific community from 20 different countries, so we thank you for sharing not only your science, but also your personal philosophy and your vision and inspiration. So please join me in thanking Professor Bawendi for the inspirational lecture. Thank you.
Thank you, sir. It was a wonderful interactive section. Now, on behalf of organizing committee, I would like to call upon organizing chair, Dr. A. Nirmala Grace, to felicitate our honorable chief guest and the session chair.
Thank you. Thank you. Very good. Thank you.
Chirantan Rasayan Sanstha, which is an esteemed and prestigious society of Indian scientists located at the Vidyasagar University, West Bengal, felicitates our Honorable Nobel Laureate with his prestigious Lifetime Achievement Award. This will be performed by the Secretary of CRS, Professor Yel Magad, and the Organizing Chair, Dr. A. Nirmala Grace. We request the audience to kindly rise to honor the Nobel laureate. Can we please have a huge round of applause?
We would now like to request the Nobel laureate, Professor Bawendi, to honor Professor Ajay Vinu with the CRS Gold Medal.
Can we please have a huge round of applause? Thank you for your patience. Please be seated.
As we conclude today's gathering, we thank each one of you for lending your time, attention, and expertise. We request all the ICNAN speakers and participants to gather in foodies for lunch. Vehicles have been arranged outside for the speakers.
We
Thank you.
request the school students to assemble in CS Hall, and we look forward to seeing the guests and the delegates in the upcoming sessions. On that note, I'm your host Vidit.
And I'm your host, Leah, signing off.
It was a wonderful talk.
I repeat, we request the school students to assemble in the CS Hall. I repeat, we request the school students to assemble in the CS Hall.